Okay, welcome to video 2.6 in kinematics. We're getting horribly off in terms of the numbering, but that's okay. We want to deal with the special case called constant acceleration. And you did all kinds of problems about this last year, so you know the kinematic equations. We're going to derive them via calculus. And we're going to say, well, actually, we're not going to yet because we don't know the antiderivative. But you do remember that if the acceleration is constant, there's really only 5 variables. You have t, the time. You have delta x, the displacement. You have v naught, the initial velocity. You have v, the final velocity. And you have a, the acceleration. And there are 3 equations that relate to 5 of these. There is the first kinematic, which says v equals v naught plus at. There is the second kinematic, delta x equals v naught t plus 1/2 at squared. And there's the third kinematic, v squared minus v naught squared equals 2a delta x, which can actually be derived by taking the first 2 kinematics and using algebra. One thing you should have noticed, though, is that the first kinematic is simply the derivative of the second kinematic. Derivative of v naught times t is just v naught. Derivative of 1/2 at squared is just at. And we'll do a couple of examples, and then this video will be over. Our first example. A rock is dropped off of a certain bridge. It spends time t in the air before hitting the ground. If the height of the bridge was doubled, what will the new time in the air be? So the first thing we have to recognize is that this is free fall, which you should remember is constant acceleration. And a equals 9.8 meters per second squared downward. So we'll draw a picture of this. Here's the bridge. We'll call the height of the bridge h. The initial speed of the ball is 0. And so what we're trying to do is we're trying to relate the height of the bridge to the time in the air. So h and t. Keeping v naught equal to 0 and keeping a equal to, I'll make that positive g, and then we'll define downwards to be positive. So the equation that has all these in it is the second kinematic equation. Delta x equals h, a equals g, v naught equals 0, and time equals capital T. So we say h equals 0 times t plus 1/2 g times t squared. That first term is 0 and goes away. So we can see that h is proportional to t squared. But we want to know what the new time in the air is, so we need to solve for t. T equals 2h over g square root. So if you double h, the question is what happens to t? So h becomes 2h, and t becomes 2 times 2h over g, which we can rewrite as the square root of 2 times 2h over g, which is just the original time times the square root of 2. Problems like this show up all the time. You need to become comfortable with them for AP. Once you have this equation, it's pretty easy to do the rest. You see, oh, well, h is under the square root. So if we double h, t will increase by a factor of square root 2. If you wanted to double the time, h would have to increase by a factor of 4. Now, sometimes you'll have problems with two objects. These usually require a bit more ingenuity, but they're really not any more difficult as long as you keep clear track of which variables go with which objects. This is an example from your textbook. We've got a red train. It's traveling at 72 kilometers per hour. A green train traveling at twice that speed are headed toward one another on a straight line track. When they're 950 meters apart, each engineer applies the brakes, and both trains decelerate at a rate of 1 meter per second squared. The question is there a collision? So the first thing we'll do is we'll get everything into meters, seconds, and so on. So 72 kilometers per hour, that's 20 meters per second when you do the conversion. And 144 kilometers an hour becomes 40 meters per second. The next thing we'll have to ask is, okay, they start out 950 meters apart and they slow down. As the red train slows to a stop, it's going to travel a certain distance. As the blue train or the green train slows to a stop, it will travel another distance. If those two distances together are less than 950 meters, they will not collide. So an example would be position and time. We've got the green train like that, and the red train like that. Notice in this case, there's no collision. The distance traveled by the green train and the distance traveled by the red train do not together equal 950 meters. If, on the other hand, our graphs look more like this, where there's the distance traveled by the red train, and here's the distance traveled by the green train, those two distances in this case are greater than 950 meters, and so in this case, there's a collision. What we want to do is find out which of these two graphs is more accurate. And we'll use the kinematics for this. The distance traveled by the red train can be given with the second kinematic equation, or pardon me, the third kinematic equation, because we don't know time here and we don't really need to. So we'll say v squared minus v naught squared equals 2a delta x. Wait, that's not true. V is 0 because the train is slowing to a stop. V naught is 20 meters per second. A is -1 meter per second squared. And we're looking for delta x. So delta x equals negative v naught squared over 2a. So negative 20 meters per second squared over 2 times -1 meters per second squared. And that makes the distance traveled by the first train 200 meters. Now the green train, on the other hand, is moving twice as fast. We'll use the same formula to figure the distance it travels. And so that's going to be negative v naught squared over 2a. We could put the numbers in. When we do, we'll get 800 meters because it's going 40 meters per second instead of 20 meters per second. But the other way we can think about it is, well, delta x is proportional to v squared. So if you double v naught, you're going to quadruple the stopping distance, and so 200 times 4 is 800. Notice that 200 plus 800 is greater than 950 meters. The result is that the two trains will collide. What's more, you can see that the red train will stop quickly, and so the collision will occur at 200 meters, right there. The green train will still be going not super fast, but there will be a collision and it will be bad. For tomorrow, you should be able to do questions 2 through 4 and also 6 and 7. Those are all questions. The qualitative ones, that's what I will be checking